Welcome to springlib.
Hello everyone, today we're doing chapter 11, problem 44, and this problem asks us to determine the structures A, B, C, D, and E in the following reaction scheme. And we're given the reagents for every step, and we're given the final product. So in essence, this is a retrosynthesis problem. So we need to start from the product and work our way backwards. So here we see we have this compound with an alkyne here and an extra carbon here. So the reagent to get to this is some sort of alkyl halide. So we have one carbon here, and attached to that is iodine, iodine being one of the halides, so it's a leaving group. So we have an electrophile here. So that means that in order to get this molecule, two things had to happen. We had to add an extra carbon, because when we do an SN2 reaction, we pick up this carbon here. So that means that the starting material to get to this product has to have one less carbon. And secondly, we need to have a very strong nucleophile to attack this product. So the only carbon that you can think of is this terminal carbon, because we know that we can make an alkyne into a nucleophile. So working our way backwards, we know that we had to pick up a carbon, so we have to lose one of these carbons. And which one? Well, it's trial and error. So if I lose this carbon here, I know that this alkyne I can make into a very strong nucleophile by adding either a deprotonating agent, so sodium hydride, which can abstract the proton to make a carb anion here, or NH2 minus, or any some sort of salt of this version. So we know that the nucleophilic version of this would be with that proton removed. So then those two electrons of that sigma bond would go on to make a carb anion, which would nucleophilically attack this. So, actually here you see that the step preceding this is our NH2. So we know that NH2 would deprotonate our alkyne to form our nucleophile E. So we know that this is structure E. And therefore, because we deprotonated it in a step before, this is our structure D. So right away, by working the backwards, we already got two of them. So now from D, we need to get C. And let's see what we have. So let me redraw D here. So I redrew D. And here we have some sort of oxidizing agent and two equivalents. And the step before, we add two diatomic bromines. We add 4 bromines. So when you see this reagent here, this is an oxidizing agent. So from an alkane, so straight bond, you go to, with one equivalent, to an alkene. But here we have 2 equivalents. So from an alkane, we would go to an alkyne, 3 bonds. So we know that this is how we made D. We made this alkyne using 2 equivalents of this oxidizing agent. But what was the starting material? So if we use 2 equivalents, that means we know that we had to start with an alkane, a straight bond, right here. But is it any sort of straight bond? Well, the step to get to C has 2 equivalents of Br, so that means that we need to just start with some sort of pi bond here, so we can nucleophilically attack these diatomic halides to add them on. So because we know we added these 2 Brs, let's draw these 2 Brs across the double bond where we want, or the triple bond where we want. So 2 Brs on each side. And how do we get this? Well, we had to add this over an alkene. So we got this, so this will be C. So how do we get C? Well, in order to have something react with bromine, we need a nucleophile. But we need a nucleophile without changing any carbons or changing any properties of the atom. We just need to play with the bonding. So if I add a double bond here, we can see that, yes, we can add and pick up the bromine groups. And actually, sorry, it's only one equivalent of this Br. It's only one equivalent. So we know that each side is only going to have one of these bromines. If there was 2 equivalents, then we would get 2 on each side. But because there's only one equivalent, we're only going to get one of these bromines on each side. And that's C. So how do I get this? Well, if I react my ketone with Br, we know that we would pick up a bromine, and we get a secondary carbocation with this bromine here, and a bromide ion that can attack this side. So that's how we get C. So we know that B, yes, indeed is correct. But now we use the same oxidizing agent, but only one equivalent. So now it means that we know that the product is an alkene, and we use one equivalent. So that means we have to start with an alkane. So we know that A has to be some sort of alkane version with the same number of carbons, but we need some sort of leaving group here to work, because you see here when we used these two equivalents here, we had two leaving groups. We had one bromine here, one bromine here. So when we oxidize it to the ketone, to the alkene, we lost an equivalent of bromine, but one remained. When we add the second equivalent, we lost a second equivalent of bromine from the structure. So we know that we need some sort of leaving group here. So we can add any halide on this molecule. So we just designate it as X, but X can equal bromine, chlorine, any halide to get A.